Starting with the feature-based explanations, we have one possible definition here. So feature-based explanations, they denote how much each input feature contributes to a model's output for any given data point. And it achieves that through score or ranking over the features. So why would we want to use a feature-based explanation method? Well, it can help us identify dominant features that contribute to the prediction, and that also conveys relative importance of the features to the model's output. Example methods now for feature-based explanations would be gradients, Shapley or Shapley values, and we're actually going to have a look at those in just a moment. Using Shapley values for explanations is indeed very popular in machine learning, but actually Shapley values describe a game of n number of players, and we're going to restrict that to 3 players for now. So we have 3 players, P1, P2 and P3, and they're all playing a game together. The total reward of the game is going to be $1,000 and the 3 players that we have, they can enter the game in arbitrary sequence. So it could be that player 1 enters the game first, player 2, player 3, and so forth. All possible permutations are allowed. The reward or the winnings that the players take home will depend on the combination of players. And we will have a different reward based on which players contribute to the game. Let's look at the game step by step, and we're going to start with the first coalition where there's no player playing the game. So if nobody's playing the game, then the reward value will be $0. On the other end of the table, we have coalition number 8. So that will be all 3 players, player 1, 2, and 3 playing the game. And we already know that the maximum reward that they can get if they all collaborate is $1,000. And then we have the values in between, where obviously each player individually could be playing the game. So player 1 playing by themselves, they would get a payoff of $25. Player 2 and player 3 seem to have skills that better match the game, so they can earn $100 and $150 respectively. And now we can start forming coalitions in between players as well. So we could have player 1 and player 2 playing the game and getting a reward of $550. We could have player 1 and player 3 playing to get $650. And then we have player 2 and player 3 only getting a reward of $50. So they might have a very overlapping skill set. So combining the 2 of them is not going to give a big payback. So we have the set of players, player 1, 2, and 3. And S now is going to denote a subset of players. So for example, one possible subset could be player 1 and player 2 combined. And Shapley value, the payoff of player P subscript I, is now going to be the marginal contribution to all subsets where the player is not contained themselves. So in an equation, it looks like the one equation that you see below, where you have the sum over a particular subset where the player Pi is not part of it. And then we have a weighting factor and also the value function itself. So this is now just taking the equation and breaking it down into the individual components. So we have to look at the number of ways subset players could have entered the game. And then we already said that underneath the summation, we have the subset that does not contain the player Pi. And then the weighting factor is going to be how many players out of the total number of players are in any given subset. And then the value function will describe how much bigger the payoff is if we add player I to this particular subset S versus having this set without the player I. So moving now from players to machine learning, well, the game that we're playing is going to be the model itself. The players, well, those are going to be our features. And the idea is to build the best performing model, obviously. And now with the context of explanations, what we want to find out is how much are different features contributing to a certain prediction that the model makes. So the total payoff now is the model output on the original input. And coalitions are going to be the different versions of inputs where certain features are removed. So you could train a model with 10 features, with 15 features, different combinations of the features as well. And removing of the features is actually quite difficult to do in machine learning, because once you train a model, that particular value is going to be expected to be part of the input feature set. So dropping off players or removing players from the set that you want to analyze, that's going to be hard. So what we need to do instead is we need to replace any missing values, so we can simulate dropping off features or players by replacing with a baseline value of that feature. And just to note here that there are actually more sophisticated versions of how we can go about removing those features as well. But for our purpose, we're just going to assume that if we were to drop a player from the game or remove a feature from the prediction space, well then we're going to have to replace it with a baseline value. Shapley values now, they have certain axiomatic properties. First one being that a feature that does not contribute to any coalition should get a 0 importance value. Secondly, all feature attributions must sum up to the total model output. Next, we also need to meet symmetry, where symmetric features get the same attribution. And finally, we also have the axiom of linearity, where attributions of the weighted sum of two games is the same as the weighted sum of the attributions of each game. So Shapley values follow these axiomatic properties. And we're going to look at Shapley values or Shap values in a notebook now. In this notebook, you'll see a visual representation of the Shap values, where certain Shap values will have a positive contribution, certain values will have a negative contribution. So we're starting off with a base value, and then the positive and negative Shap values will move the value up or down, and we're going to end up in a final position, and this is going to be our predicted value. So we can see by how much the different features will have shifted the prediction away from the baseline or the expected value. The next type of explanation method that I want to talk about are so-called instance-based or example-based methods. And example-based methods are model-agnostic explanation methods that either quantify the value of instances for a model prediction or the parameters of the model, or surface examples from training set, leaning on users' interpretation of those examples. So why would we want to use example-based explanations? Well, they are really rather effective for explaining complex concepts. And also, there is a tendency in humans to prefer natural alternatives. So we had a look previously at Shap values, and those are not necessarily natural explanations. Examples are a very easy way to digest an explanation of a model. However, we certainly require the instances and the examples to be interpretable, and that can indeed be very difficult for high-dimensional data point examples. So let's say you have one particular customer. That customer may be described with 50 different features, different attributes that this one particular customer has. So even if you provide an explanation, you would have to describe 50 different features potentially. And that again might be too much to digest as an explanation. A quick distinction here. So first of all, we should not confuse outliers with influential instances. And we also have a list of example methods here. So one example on how we can get an instance-based explanation would be through so-called deletion diagnostic. We can also come up with influence functions. We can look at data Shapley or counterfactual examples. And we're going to look at deletion diagnostic first, where the motivation is that individual data points are influential if their presence or the absence of that particular data point causes changes in the model parameters or predictions. So if you think about a data set and you train a model, you would get a set of weights or parameters depending on the type of model that you choose. And obviously those weights and parameters will depend on the training data that was used. So the influential instance now would mean that if removing that instance leads to a very high change in that parameter or even in the model output, well, then you have a very important example that you can use as contrastive explanation. So how can we find these important instances? Well, we can delete iteratively different instances from the training data and retrain the model, and then simply observe, do the parameters of the model or the predictions change? Careful though, this actually requires retraining of the model after we've deleted some of the instances, so this is not an efficient way necessarily to go about it, especially if the model training itself takes up a large number of resources. A quick example here though, so we have a model that was trained on the tabular data on the left-hand side, and then we're deleting the final data point to see how much do the weights change, and do we even get a different output prediction. And it happens that this particular instance was rather important because we can see that the weights are changing. Finally, I want to talk about concept-based explanations, or explanation methods that derive understanding by detecting concepts that are embedded in the so-called latent space that is learned by deep neural networks. So this is a rather advanced topic, so I'm just going to give a high-level overview. The idea is that feature-based isn't necessarily user-friendly, and instance-based explanations struggle with high dimensions. So what we want to do instead then is we want to prescribe certain concepts that we want to identify in the latent space, and then give explanations on the back of that. So what could be a concept? Well, it could be an abstraction of a feature such as the curliness or stripedness in an image. And once again, we have a couple of example methods here, TCAF or ACE being some of them. Finally, I want to warn you about some of the common pitfalls when it comes to using explanations. And the general takeaway here should be that you should not rely blindly on explanation methods. In particular, you should be aware of confirmation bias, the lack of faithfulness of the explanation to the true description of what the model is doing, maybe the lack of interpretability, and also there could be biased explanations that are generated. Confirmation bias is actually quite prevalent in machine learning, because even when it comes to exploratory data analysis, you might be looking at outliers and thinking, well, those data points look weird, I should delete them. And this is just using your past beliefs and your own hypothesis, and maybe what you're doing is you might be removing outlier or minority communities as a whole. The second concept is the lack of faithfulness. So we said the explanations, for them to work, they need to be a true description of the model behavior. So the ability to accurately explain the function that was learned by a model. And explanations, we said they need to mimic the behavior of an opaque model. So if we have an explanation that looks good but is not faithful to the model itself, well, then it cannot be used. Next, we have lack of interpretability. So explanation methods, they can produce results that are faithful but not necessarily interpretable or plausible. So imagine that you're creating an explanation that is a very long, very complex mathematical description, maybe even the full equation. You could think about the model itself. You could just provide the equation as an explanation, but that's not necessarily understandable or interpretable by lay individuals. So we need to quantify how easy it is to understand and reason about the explanation, and that usually comes down to how many rules we have and how many features are being used. And generally we should limit the number of rules and number of features as much as possible to make it able to digest the explanation. Finally, we can be facing the issue of biased explanations. So just like how models can be biased, explanations themselves can also be biased. So perception and cognitive bias can lead to a misalignment between a causal chain of decisions and the attribution of human behavior to the interpretation. What we have here in this chart is a classifier, and again in the triangle and square you have a overlaid attribute value of female and male, and then you might be producing a linear explainer as a helper method. And what you can see here is that the performance differs for the different attribute values. So beware when creating explanations, just like you need to check the model performance for the different attributes and different subpopulations in the dataset, you should also check how well do the explanations work for different subpopulations.